Hello students, this is Naren Kumar Devedi welcoming you all in today's lecture, starting with first topic, variable capacitors. So basically variable capacitors are those capacitors in which the effective area of plates can be adjusted. So such capacitors are said to be variable capacitors and whose values can be adjusted by changing the effective area of plate. So depending upon their functioning, they have got different applications in industry too. So the very first type of variable capacitor is variable air capacitor. Variable air capacitor. In such capacitors, the plates are made of brass or aluminium. The plates are made of brass or aluminium, and the dielectric used is oil, and the dielectric used is oil, or as per the name suggests, air, or there may be mica. So in variable air capacitor, parallel plates will be made of aluminium material or brass, and the medium in between those plates will be taken as either oil or air or mica. Now see if the capacitor is made from a pile of small n plates of alternate polarity, each having area capital A and separated from adjacent plates by say a distance small d, then the capacitance is given as C equals to n minus 1 into epsilon naught A by D. So placing the value of n here, effective area, and D, we can have the capacitance of such an arrangement. The second type of variable capacitor is multiple capacitor with a mica dielectric. In such capacitor, actually the plates of capacitor are made of say tin foil, and these are arranged in such a manner that alternate plates are formed like this, and here we have dielectric material. So let me just draw this one, and there is also mica and dielectric, and say this is T. These are tin foils. Now let me just level this tin foil, and this dielectric taken is mica. Third type is paper capacitor. Now it has dielectric of paper impregnated with paraffin, wax or oil. So I am just drawing to have a brief idea. Like this, and here from we have this thing. So here the dielectric will be taken of paper impregnated with paraffin, wax or oil. So this is the paper dielectric being taken in between the plates. Like this. Now one more thing, here from also you can have a dielectric like this. So here let me level it. This is paper impregnated with paraffin, wax or oil, and the papers are being rolled and sealed into a cylinder of relatively small volume. Now this is tin foil. So this way the paper capacitor is formed. Now fourth type of variable capacitor is electrolytic capacitor. Okay, so in case of electrolytic capacitor, such capacitors are made. These are made by passing direct current between two sheets of aluminium foil with a suitable electrolyte or liquid conductor between them. An extremely thin film of aluminium oxide is then formed on the anode plate with the anode plate which is on the positive side of DC supply. Now this film is an insulator and forms the dielectric between the plates, the anode terminal is marked in red or by positive sign. So this is about electrolytic capacitor. Let me just read it out. What have I written? These are made of passing direct current, DC current, between two plates, between two sheets of aluminum foil. Means there will be two plates of aluminum foil taken, and between those two the DC current will be supplied, and there will be an electrolyte or liquid taken in between those two sheets of aluminum foil, and the electrolyte or liquid conductor between them taken is when that DC current is supplied, then that liquid or electrolyte material taken in between forms an extremely thin film of aluminum oxide, which actually serves the purpose of dielectric in between that those two sheets or plates. So that the film is an insulator and forms the dielectric between the plates, and the anode terminal is marked just to have clear identification, because such capacitors are given or are connected with proper polarity. Otherwise, it's quite dangerous in a circuit. So, just for the identification purpose, the anode terminal is marked in red or by positive sign. Now, let's have a look. So, that it's a general look of electrolytic capacitor. So, these are two aluminum sheets given positive and negative polarity, and in between there is electrolyte material, and a thin film of oxide, aluminum oxide, is formed here, which is towards positive side or anode side of this arrangement. And let me level this. This is electrolyte, and here oxide layer. This is actually anode. So this is generally electrolytic capacitance. Let's have next topic, capacitance of a parallel plate capacitor with and without dielectric medium between the plates. Means a parallel plate capacitor first will be taken without any dielectric medium in between the plates, and later on we will be having the same parallel plate capacitor with dielectric medium in between. How the capacity of that parallel plate capacitor changes? By placing the dielectric medium. So a parallel plate capacitor is what? It is the assembly of two conducting plates separated, kept parallel to each other and separated through a distance which is very small in comparison to the physical dimension of the plates. So let me write the definition first. So such capacitor is formed by placing two conducting plates separated by a distance which is small compared to the linear or physical dimensions compared to the linear dimensions of the plates. Okay, so how does it appear like? Say these are two plates conducting plates being taken parallel to each other and kept in very small distance, small d. So this is plus sigma surface charge density, positive surface charge density of this left plate on which positive charges are given. Now when this plate is brought close to an uncharged plate, so there is charging by induction and negative charge, surface charge density appears here and the outer surface is grounded. So this makes a parallel plate capacitor. Now here we write the electric field intensity, the electric field intensity between two closely placed plates is between two plates, I must clearly mention in plates in vacuum, is equals to sigma upon epsilon naught. Actually here we are having vacuum, no dielectric medium has been taken yet, and in that the electric field intensity between the plates is written as sigma upon epsilon naught. Now that is surface charge density sigma can be written as Q by A. So we may have this as Q by A. So epsilon naught A. This is electric field intensity. Now moving ahead, since this electric field is uniform between this region, between the plates, so the electric potential we can now write the potential difference between the plates is, how do we write electric potential? So that V equals to E into D, and we can have this value back here. So having that, we may have Q I must write D upon epsilon naught A. Now you can have this V here. Hereafter we can talk of capacitance. So the capacitance C equals to Q upon V. So here from we can have this Q upon V, epsilon naught A by D, epsilon naught A by D. So this is the capacity of the capacitor without dielectric in between. Now moving ahead, we can have the dielectric now in between if the space between the plates is filled with a medium of dielectric constant, say K, with dielectric constant K, then we can write the capacity in that medium Cm equal to K epsilon naught A by D. So this will be the capacity of the capacitor in the medium having dielectric constant K. So now where this K value can be further written as where K equals to Cm upon C naught, or you can have this Cm equal to K into C naught, and therefrom you can just have the value of C naught back here. C naught we are calling this. Fine. So this is K times epsilon naught A by D. Now what else you can say about this? This may be you can write it to be K is epsilon or relative permittivity also is the same dielectric constant. So here you can write epsilon R, epsilon naught A by D. So this value you can write relative permittivity A by D. Let's have next topic, spherical capacitor. Spherical capacitors are those capacitors which consist hollow spherical conducting sphere surrounded by a conducting shell, spherical conducting shell. So let me just define it. These consist of a hollow conducting sphere surrounded by another conducting spherical shell. Now let me just draw the diagram so that we can have the brief idea of the statement that has been written now. Suppose this is the hollow conducting sphere on which we have positive charges on its outer surface like this, and say the radius of this be say R A and the sphere be say A, and it is surrounded by another spherical conducting shell concentric with this hollow spherical conductor. Now the surface of this shell will have negative charges here, and the outer surface of this shell will be grounded, earthen, so that to form this spherical capacitor. Now the radius of this outer spherical shell is being taken as RB, and this is B. Now the electric field obviously will be directed like this. So these are electric field lines that are being drawn now. So such electric field lines will be seen. Now let's calculate the capacitance of this capacitor. Now we write the potential of inner sphere, this sphere is written as VA, which is equals to Q upon, actually the potential will be due to this sphere as well as due to this, the sum of that will be the potential. So Q upon 4 pi epsilon naught into, what's the radius of this? It is RA. Now this is having negative charges, so the potential due to this will be negative. For that reason I am writing minus Q by 4 pi epsilon naught RB. Now you can have Q as common term, so Q upon 4 pi epsilon naught will be a common term, and here you can write 1 upon 4 pi 1 upon 4 pi epsilon naught has been taken out, so you can write it here 1 upon RA minus 1 upon RB. So this will be actually I must write this to be the potential difference actually. So here you may write the potential difference potential of inner sphere. It won't be right to say the potential difference you write now. The potential difference. So this has to be this one, because here VA would be equals to 1 upon 4 pi epsilon naught Q by RA, and VV potential due to the outer shell would be 1 upon 4 pi epsilon naught minus Q upon RB. So better would be to say the potential difference. So this is the potential difference actually due to that. So now we can talk of capacitance. So here the capacitance C equals to Q by V, and that is equal to, actually here if we have the LCM, so it would be RA into RB, and here RB minus RA. So directly having the value now with us, 4 pi epsilon naught RA RB upon, it would be RB minus RA. So this will be the capacity of that spherical capacitor. Let's have next topic, capacitance of an isolated spherical conductor. Suppose we have with us an isolated spherical conductor like this, and say the charges spread on its surface are say positive. Now we have charges, and the radius of this spherical conductor is being taken as small r. So now we can write the potential first on the surface of this conductor, potential at the surface of the sphere is V equals to 1 upon 4 pi epsilon naught epsilon r into q by r. Actually here the medium is being taken, so it's the relative permittivity of that medium in which that isolated conductor is being taken. Now the capacitance can be written as the capacitance C equals to Q by V, or you can have Q upon, now the value of V is being written 1 upon 4 pi epsilon naught epsilon r into Q by r. So just this implies that C equals to 4 pi epsilon naught epsilon r into small r. So this would be the capacity of that conductor. Now moving ahead, you can further proceed this for vacuum. Actually this relative permittivity of vacuum is 1, epsilon r equal to 1. Therefore C now is 4 pi epsilon naught into r. Else you can have it as r upon 1 upon 4 pi epsilon naught. So this 4 pi epsilon naught can be written as small k. So here you can write r upon small k. So therefore, now further you can write in CGS, what's the value of that k? Small k is 1. Therefore, in that CGS medium, the capacity of such conductor is, say, small r. Okay, now let's have next topic, cylindrical capacitor. Cylindrical capacitors are basically made of two coaxial cylinders of same length having radii RA and RB in such a manner that the outer cylinder is earthed and the inner is given some charges. So this way the cylindrical capacitor is formed, and now the capacity of such cylindrical capacitor can be written as C equals to L upon length of the cylinder upon 2 K. K is that the same 1 upon 4 pi epsilon naught log base E RB upon RA. Now where you can write where K equals to 1 upon 4 pi epsilon naught into capital K, dielectric constant of the medium. Now here I must draw the cylinder so that we may have which one is outer radius and which else is inner radius. These cylinders will be taken of same length. So like this. And here the outer will have earthing. Here actually this is the axis I must draw. This is the axis. Now the radius of this outer one is RB, and the inner radius is RA. This is RA. So this way, here actually positive charges are given here on the inner cylinder, and subsequently there will be negative charges here. So this way we can have cylindrical capacitor. The length of this is small l. So just having these all constants with us, we can just place them and get the value of capacitance of such capacitor. Now let's have next topic, combination of capacitors. Combination of capacitors, why do we need to have combination? Because as per the necessity of the time being, the capacitors are to be combined either to increase the effective value of those capacitors or to reduce the effective value of those available capacitors. So using the available valued capacitors, we can either obtain the equivalent capacitor of more value or the equivalent capacitor of less value than the available values. So let's proceed. Capacitors can be combined either in series or in parallel. So let's first have series combination. Suppose we have three capacitors of different capacity, say C1. Now second capacitor with us is of value C2. And the third capacitor available with us is of C3 capacity. Now these are to be connected in series, so the second plate of first capacitor is connected with the first plate of second, and second plate of second is connected with the first plate of third, and the second of third and first of first is connected with an external source offering potential difference of V volts here. So this is positive polarity and this is negative potential here. So on this, positive charges are here and negative will be subsequently induced here. And here also positive and negative. So this way the capacitor will be charged, but here the charges stored will remain same in all. This is the condition of series combination. Now say the potential difference across this first is V1, across this is V2, and across third is say V3. So the potential applied will be just equal to the sum of these three potential differences at the ends of C1, C2 and C3. So let's start. So we write now, since V equals to V1 plus V2 plus V3, now we can have this, suppose this combination of capacitors is replaced by a single valued capacitor whose capacitance is say CS, C subscript S, and is connected with the same potential difference source. So the potential across that equivalent capacitor having capacity Cs is written as Q upon Cs, which is equals to, here V1 will be written as Q by C1, here Q by C2, here Q by C3. So taking Q common from right hand side and cancelling it with from left hand side, we can have 1 upon Cs, which is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Let's generalize the case. For n capacitors in combination, you can have 1 upon Cs to be equal to summation over I equal to 1 to n 1 upon Ci. Okay, now let's have second type of combination, and that is a parallel combination of capacitors. Again, say we have three different capacitors. Now the capacity of this is say C3, this is of C2, and this one is having C1 capacity. Say these are being connected in such a way that the first plate of all such capacitors are connected together, and the second plates are connected together. So such combination is called parallel capacitor, parallel combination. And now say these are given the potential of V volts. So here positive and here negative. So all such left plates of all these capacitors will have positive charges, and the right plates will have negative charges. So this way the capacitor will get charged. Now here the potential applied will be equal to the potential appearing here across the plates of first capacitor, and the same potential will be appearing across the plates of second capacitor, and the same will appear across the plates of third capacitor. So here the charges stored will be of different values. So these are charges being stored across the capacitors connected in parallel. Now say this combination of three capacitors is replaced by a single capacitor having capacity as Cp and is further fed with the same potential difference source. So as per the conservation of charge, we can write Q equals to Q1 plus Q2 plus Q3. You can write. Now this can be written as, this is the value of charge stored in that single valued capacitor representing this combination of three parallel capacitors. So you can write Cp into V equal to C1 into V plus C2 into V plus C3 into V. Now taking V common from right hand side and cancelling it with left hand side V, we can have this C1 plus C2 plus C3 as the last outcome. Now for n number of capacitors in combination, we can say Cp is equal to summation over I equal to 1 to n Ci. Okay students, so with this we end up today's session. Do like and subscribe the channel.